Hi, welcome back. So we've so far talked about disk method and washer method for finding the volumes of solids of revolution. But we need one more method to use in case those methods fail, or in cases where it just doesn't work to use washers. So we're calling this shell method, and you'll see why in a bit when we talk about what it looks like. But let me give you some motivation first. So the idea here is that sometimes disk or washer method will be really difficult. And truthfully, it might be so difficult to do that it's actually basically impossible. I don't like to say things in math are impossible because, if we manipulate things enough or come up with an alternative, we can usually do anything. But here it might be basically impossible. So let me show you an example of why we need an alternative method. Let's say on my axes here, I am trying to revolve around the y-axis the graph of sine. And let's say I'm just looking at this first part, but you can imagine it continues on. So we're taking this first portion and I'm trying to revolve it around the y-axis. So our method so far for doing this, and let me label this really quick. This is y equals sine of x. Our method for doing this involves taking washers and finding their volumes and then adding them up. So because we would be revolving around the y-axis, we would have these sort of horizontal bars that are drawing out these washers. So it looks like maybe we could do this, I understand the concept, but we come up with this issue where we're trying to find the outside and the inside functions. I don't really know what's going on, because what are the outside and the inside here? So just like when we compute areas, sometimes we need to change the method because we don't have a clear above and below function. So it would be really helpful to us here if we could use vertical bars instead of horizontal ones. So it would be nice if we could have vertical slices instead of horizontal. With vertical slices, we could use sine of x as the top function, and then we could just have the horizontal axis as the bottom function. So doing this would be really nice for us and it'd be a lot easier to do. So this is where the shell method comes in, and so we're going to start looking at changing the orientation of the bars and drawing shells instead. So let's talk about what that looks like. You can see a little preview of what we're going to do down here, but the shell method, rather than using disks or washers, allows us to add the volumes of shells. So instead of stacking up things like we do with disks or washers where we sort of stack them all up, here we're going to be layering things. We're going to take one shell and then we're going to layer another shell on top of it, so sort of build out the shape we want to do. So we use this specifically in instances where we want to use vertical bars to rotate around y. So if we're rotating around y with a vertical bar, we would use shell method. Or we would also use this if we were rotating around x and we wanted to use horizontal bars. These would be dy. So we use shell method whenever we're doing these things, and the reason why is you can kind of think of these shapes as drawing out shells. So if we look at this first version, this first shape is going to sort of circle around on itself and draw out this shell. And I've drawn it down here. It's sort of like a cylinder with a hole in the middle. It's just and it's really small since it's just a little dx width. And so it draws out this shape as it goes around, and it's this shell. The same thing would happen with respect to y. You can imagine this little shape sort of going around the y-axis, and it's drawing out these shells as it does so. So it'd be kind of hard to visualize. I think the more that you've thought about it and the more you see this, the easier it gets. But we're just taking these little pieces and drawing out these outside, sort of I think of it honestly, I almost think of it as like rolling up toilet paper. These almost look like toilet paper rolls. You're taking a little itty bitty sheet and just rolling it around and then going another layer out, and eventually you're making this larger shape. So this is the method we are going to use Instead of discs or washers, we're going to use these shells. So we're going to go through the process for deriving this formula. So it takes a little bit more work than the disc and washer method, but not too much. So I'm going to derive the x formula for you, the respect to x formula, and then I'll give you the respect to y formula as well. And again, you're going to see a little preview of what we're going to do here. Remember, we are going to add up the volume of shells here to create the full volume of the solid. Okay, so let's draw an example of what this graph might look like. I'm going to do the revolving around y version, which is going to be with respect to x, because our bar is going to be vertical and have a little width of dx. Okay, so let's say we have some function on the top of this that represents the height, and then we have this inside function here that represents the bottom part. So let's say we have g of x and f of x. And we're going to just look on this smaller interval here. Let's say from A to B. So this weird shape is kind of being revolved around the y-axis, and we're going to take these little shells to build it out. So this is going to use, I'm going to kind of expand on it with this picture here. So we're taking that little bar and revolving it around this shell in the way I've drawn here. So it's going around this shape, and we're making this shell. And in order to find the volume, what we're going to do is unroll it. So I'm basically taking this shell and unrolling it. So I'm putting a cut in it and then unraveling it down. You could think of like a piece of paper wrapped up into like a cylinder. You could like unravel it down flat. So here we're going to find the volume of it now flattened out to find the volume of the shell. So okay, we want to find this volume. So we're going to need a length, a width, and a height. So let's start with the things we know. So this little width here, I guess, is a dx. Maybe it's like the depth. And that's because of this little change in x we have for the width of the rectangle. Then we're going to have the height of the cylinder, which is going to be the top function, that's my f of x, minus the bottom function, that's my g of x. So that's this whole height. You can look here on our shape. We do the top minus the bottom to get the height of the rectangle, and it's changing depending on the x value we're using, but we do the top minus the bottom, the f minus the g. So then we just need this other length, and this, if we compare it to the cylinder, is just the circumference of the cylinder. So circumference is 2 pi times the radius, and so radius is what we're going to need to figure out here. In my opinion, this is the trickiest part of the entire thing, is this radius bit. So as we take cylinders, we're starting with cylinders really close in, and then we are moving them out slowly. So the cylinders, or these shells, have radius that is changing. So it starts as like maybe a small radius when we're really close to the axis, and then it's moving outward and it's becoming a bigger radius. So our radius is changing, it's not constant, because the shells are getting larger as we build out this volume that we're making. So the radius is just the distance from the center where we're rotating out to whatever point we're looking at. And really, this is just x. So we're going from the 0 on x to whatever our x value is that we're looking at, and that's where our bar is located. And so we really just use x as the radius. Then we can encounter some like kind of complicated problems where the radius isn't x, but I don't really like to do those ones. I like to just focus on revolving around the x or the y axis. And here, the radius is x. So our circumference is 2 pi x. Then we can find the volume of this rectangular prism, which is the volume of each cylindrical shell, and then we will add them up. So for the shell, we've taken the shell and we've unraveled it, and now we're just going to find the volume of this little piece. That is going to be the width, so the 2 pi x, times the depth, which is the dx, times the height, which is f of x minus g of x. So I've just taken those parts and multiplied them all together. It's kind of like length times width times height. And then to finish it off, we're just going to use an integral, the power of integrals, to add them all up. So we start at our first point and we go to our last point. That's because we're taking these little bars and running from A to B. And then we add up everything that we have inside. So I have the 2 pi x, that's the circumference of each shell. I multiply it by the height of each shell, which is f of x minus g of x. And then I multiply by that little depth, or sort of like the width of each shell, that's the dx. And here we go. So this is our formula for using shell method around the y-axis. So what's noteworthy here is that it's around the y-axis, but we have x's as our variables, so it's sort of what sets the shell method apart. So normally, if we were revolving around the y-axis and we wanted to use disk or washer method, we'd have to use dy. But using shell method allows us to revolve around the y-axis and use dx. So that's where it becomes handy, is when we want to use dx, but we're revolving around y. So the formula is going to follow really similarly for y. Everything's going to follow, it just has the variable swapped. So I'm just going to write it out here, and you could go through what that sort of looks like if you want. I'll put it in the notes, but it all follows really similarly. So we go from A to B on the y. Now instead of x being the radius, it's just whatever the height is of where we are at in our cylinders. So we're at y. And then we have our circumference, f of y, we have the height of each cylinder, f of y minus g of y. Wow, I'm full of typos right now. dy. So literally, so many words, just to tell you, it's the same formula. You just shake up the variables. So instead of x, you have y. And there we go. This would be the shell method for revolving around the x-axis. And again, if you have to revolve around the x-axis, but you'd really rather use dy as your variable, you'd rather integrate with respect to y, this is the method you should use. Okay, so I'm going to go through an example in the next video. That's it for this video. Thanks so much for watching, and I will talk to you in the next one.